Hello everybody, my name is Paritosh Prayagi. I'm from JI, and I'm going to talk today about customized multispectral cameras, making spectral imaging viable for mainstream machine vision business. Some words about JI, who we are and what do we do. We are a company into the business of digital cameras for machine vision, traffic imaging and medical imaging. We were founded way back in 1963. We're actually one of the oldest camera manufacturers in the machine vision business. We have presence in over 40 countries through direct offices and indirect channels. Our R&D is based out of Japan, but we manufacture our cameras in Japan, the US, and Singapore. Now let's dive deep into the topic of multispectral imaging. We've seen in the last couple of years that the number of applications that we hear and witness in the area of multispectral imaging are growing, and they are growing exponentially. We see the more traditional applications, which involves the whole food market, inspection of fruits, vegetables, nuts, grains, tea leaves, and also tobacco. And also growing into the application field of pharmaceutical and packaging, where we've seen exponential growth during the last year. Electronics, recycling, and scientific research is an area where multispectral imaging has always been relevant. And also in the business of currency inspection and all kind of security documentation, where extracting the right or relevant information from objects becomes important. But in the recent years, we've seen new applications coming up, which also see the need for multispectral imaging. These are in the area of intelligent farming and crop health monitoring processes, medical assistance systems, surgical guidance, forensics, and life sciences, extending the food market and the food applications also into the meat and poultry inspection. And then we've also seen some exotic applications out there, like fish inspection in the fish farms. But before we go deeper into multispectral imaging, I think it's very important for all of us to be on the same page on the meaning of multispectral imaging and how does it differ from hyperspectral imaging. There has been a lot of ambiguity surrounding both of these terminologies in the market, and they're often interchanged, which causes some confusion. But to draw the line straight, we can say that hyperspectral imaging is used for complete or spectral analysis or building spectral signatures from objects, whereas multispectral imaging is used more for solving targeted challenges in applications. Hyperspectral imaging typically involves hundreds of smaller wavebands which are placed next to each other, whereas multispectral imaging, there is no clear definition of how many bands is really multispectral imaging, but we can say that something typically between 2 to 15 can be termed as multispectral. When we look at hyperspectral imaging, we also see that the wavebands are equally sized, which means that there are no gaps between the wavebands, whereas the wavebands in multispectral imaging, they can be discretely positioned and they can have different full width half maximums depending on the application requirements. In hyperspectral imaging, we often see that there are many bands where we have data, but the data is not useful to solve challenges of specific applications, which means that a large chunk of data needs to be thrown off and only a part of the data is useful. Whereas in multispectral imaging, each waveband has a specific purpose in most of the cases, and that's where you use all the data that is being captured. And this talk today is focusing on multispectral imaging. Now, if you are looking for a multispectral camera, or you have had the experience of multispectral applications, it is likely that you have come across one of these methods of multispectral imaging that are commonly used in vision applications. It starts with using 2 or 3 or even more separate cameras, where every individual camera is an individual vision setup, and customers are using filters on top of the cameras to separate the wavebands. Then there is a method that we also see often. It's based on filter arrays. It's basically a single sensor approach, and the sensor includes mosaic filters on the surface through which the spectral separation can be done. The other approach that we see in the market is something called as a filter wheel camera, which includes a filter wheel that is placed in front of the camera, and you can do successive imaging by moving the filter wheel and get the required spectral separation. Then there is a method which uses 2 or 3 cameras, but then it uses a beam splitter, which basically splits the light onto 2 different sensors. When we look at the more drone-based applications, or even the farming applications, we see the approach of using a multi-sensor, multi-path is quite common. So this method basically includes individual cameras which have their own individual spectral characteristics, and they're built over multiple optical paths. But if you look at each of these methods out there in the market, there are several advantages involved, but also several challenges. For example, when you're looking at an approach with a filter wheel camera, you have a moving part in the camera, so you have limited speed capabilities because of the movement involved, and also the robustness of the camera is going down. Yeah, and you need to have an object that is static in order to have enough time to move the filter wheel and capture the same object with a different separation. If you look at a multispectral filter array, the challenge there is that you have very low spatial resolution, and basically if you have many spectral channels on the sensor, the spatial resolution is going down in a big way, which needs to be estimated or interpolated using the information from the neighboring pixels. I also mentioned the multi-sensor, multi-path approach, which is used in the drone-based applications. The challenge here is that you have to deal with the multiple paths, which means that factors like distortion, alignment, and so on are very complex, and they need to be managed in the software processing side. The most common approach that we see in the larger machine vision market is using separate cameras. But again, these are separate individual cameras, so you need to deal with the complexities of having individual setups. You have successive imaging, which means that if the object is changing its direction, or if something is moving in the object, then you don't have the same information at the same position in the image compared to the previous imaging system. So you have these certain challenges associated with each of these applications and methods. At JI, what we are focusing on is using a multi-sensor dichroic prism-based approach. Yeah, and that's the one that you see here on the bottom right. Let's look a bit deeper into this method and what is possible to do with this approach. So it's basically a prism-based approach. The advantage that you have here is that you have a common optical path, which means that the camera is, or the imaging is not dependent on or is not affected by, if the object is moving during the imaging process and so on, because in the end you have the same information on all the sensors due to the single optical path. And the single optical path also means that you have a simultaneous capture of wavebands. When using monochrome sensors at the back end, because as you see, the color separation or the spectral separation is something that does not happen on the sensor level, it happens on the prism block. So basically you have full resolution per spectral channel. You can also have a very good intensity or very good sensitivity of the system, because typically with the prism-based approach, you obviously have some loss of light that is occurring due to prism, but on the other hand, you can drive the individual sensors completely independent from each other, which means that for each sensor, you have parameters of analog gain, digital gain, exposure time, and on top of that, you have the separate spectral separation, which in the end helps to improve the sensitivity of the vision system. There is, of course, also a disadvantage associated with such an approach, and it's related to the number of channels that are possible with the existing prism designs, and also the resolution. It's not a technical challenge, it's more a commercial challenge, because in the end, adding too many sensors makes the prism system or the camera itself very bulky, and it also can increase the costs of such a vision system. But coming back to the main point, the goal here is to develop a camera system with the minimum number of spectral channels possible. Yeah. So from that perspective, this limitation is not an issue. Where is it suitable? So such an approach is suitable where spectral and spatial precision both are very important. Also where applications, real industrial high-speed applications where there is a large amount of motion involved, and also in applications where there is the issue of angular viewing, or the camera or the object is placed on a specific angle, or the object itself is of varying sizes and shapes, and these are actually the best fit suitable applications. Today, if you look at the prism technology, there are two different configurations possible. You have a 2-sensor and a 3-sensor combination. A 2-sensor is an RGB NIR combination, and a 3-sensor is RGB combined with 2 special NIRs. So the scope of combining RGB and NIR, what you see here, is limited due to the sensors that we use on the back end. We are using traditional silicon sensors today, but in the next concepts that we are building on, the scope goes much beyond NIR. So we are looking at a much larger spectral capturing capability, ranging from RGB to sphere and also beyond sphere. Now the question is, where is the difference, or what is the customization part of such an approach? So during the last several months, we at JI, we've developed a concept that we call as FlexEye. And FlexEye basically means that customers can choose their individual wavebands by following 4 simple steps. The customers can choose if they want to have a 2 or 3 prism-based camera. They can choose, what kind of sensors, what kind of resolutions are they looking for in their application. And then is the fun part, because the customers can really define the spectral band, the full width, half maximum, the bandwidth that you're looking for, and so on. And this can be decided for each and every individual channel. There's also a choice to choose between having a monochrome or a bare RGB sensor, depending on the combinations that you're looking for. And to give you a couple of examples of such applications, I would like to show you two different applications. So one is from the food business. We're looking here at sorting of fruits in high-speed sorting systems. So this is basically works perfectly fine by using limited number of channels. So what you see here is an RGB combined with two different NIRs, and the NIR bands, they have specific bandwidths. The RGB channel itself is used to look at more the surface related defects, the color, the geometrical shape and form. The first NIR channel is used to look at contours of fruits like blueberries, which are dark in color, and you don't really get a good image in the visible spectrum due to the shadowing effect and also the complexities of the light source. And the third channel is used for the more qualitative analysis of the fruit, looking at ripeness, moisture content, and so on. So you have the surface related inspection, you have the contour inspection, and then you have the more qualitative, the quantification of quality, which is done in combination with deep learning tools, which are built using common libraries that are available out there. But such an application is running at very high speed. We're talking here about more than 100 frames per second in high speed sorting application, where you need a very limited number of channels, high robust camera system, and a good enough spectral separation that works for the application. Another example that we can look at is more exotic. It comes from also from the food business, but at a very, very early stage. It's related to inspection of fish in the fish farms. This is something that over the years has become an economic problem in many countries. And we see that the number of fish farms are growing due to the growing demand of seafood. But at the same time, we see that the number of fish or the density of fish per farm is increasing. Yeah. So this leads, this overpopulation, if we can call that, leads to several issues and challenges. One of the issue is, that the fish gets the fish lice problem. So fish lice is a insect that clings on to the skin of the fish, and makes the fish very sick. Yeah, and it's really important to find out which fish is sick, because in the end the whole fish farm can be affected, and then it turns out to be a real economic problem. So using multispectral approach, the cameras can be mounted in fish farms on inspection units which are in deep sea. So these are basically lice counting systems which work again in combination with artificial intelligence. The important part here is to know is the camera is an RGB camera, yeah, but the green channel is completely separated from the red and the blue. The reason to do this is that the lice is emitting fluorescence. Yeah. And if the green channel, and this fluorescence is emitted in the green channel, and if the green channel has any kind of overlap, even the slightest overlap to any other channel, there is an issue with the spectral leakage and contamination, which makes it very difficult to identify weak fluorescence signals. Having said that, the blue and red LED are also very important, because it's something to do with the psychology of the fish. You know, it helps the fish to come closer to the inspection system. So the green is very secluded. So you see, this is a multispectral application. It's an RGB application, but you cannot use a traditional RGB camera to solve this specific problem. And that's where an approach like FlexEye becomes very important. But you know, this way, so these are two examples, but there are many such examples from, you know, a wide variety of applications. But in the end, there are hundreds of multispectral possibilities with the FlexEye approach. If you're interested to have a deeper look, we have a FlexEye configurator on the JI website. This is the link here on this page. You can have a look and also, you know, check what is really possible for your applications. With this FlexEye configurator tool, we also have an option where you want to enter something that is not available among the options, and we can also, you know, discuss those kinds of requirements. So do have a look to get a deeper insight into the concept. But having said that about multispectral imaging, a few words on JI's product portfolio in general. So the product portfolio at JI, it includes area scan and line scan cameras. We serve a very broad range of cameras, catering to many different applications, you know, looking at also many volume related applications where we have entry-level products like Go and the Go X series. But at the same time, you know, it goes up to high resolution cameras and also moving right up to multi-sensor prism-based cameras. And these combinations are for area and line scan. Looking at the product spectrally, we go from UV to sphere and also have cameras for polarization. We have also recently launched an accessories portfolio, which is starting from the lenses, because it's important to understand, you know, when we are talking about concepts like FlexEye or any multispectral prism-based cameras, in the end, there is a requirement to use a special lens to compensate for this additional glass component that you have in the cameras. But we have solutions for that at JI. So if you're looking for the right lens for your application, you know, feel free to contact us and we're happy to take a discussion with you. So with that, I'm at the end of my presentation. But if you have any questions, feel free to contact anytime, and we'll be happy to get in touch with you. Thank you for your time and have a good day.